Let's paint the scene. It's 2013, springtime, time for tax review, and a teacher decided to make one of the biggest hits of all time. Today, on One Hit Wonder, we have Corey Neiman. You may remember him from his hit single, Cheetos
Fire!
Hello, Tiger Chemist. So you just saw the teaser video to the One Hit Wonders, This Cheetos on Fire. So the video before this was the music video, so you can check that out. And today, at the end of this lesson, I will have the recap of the video on the 7th anniversary. So, calorimetry, it's an experimental technique used to measure the change in energy of a chemical reaction or a phase change. So that's really just a definition for you. So basically, what we're going to have is we are going to have a heat bath. So typically that's going to be water. So basically I'm going to have a container that's going to have water, and we are going to do some kind of physical process or chemical reaction in that water. Now the water is either going to absorb energy that is released from the reaction, or it is going to release energy into the reaction. Okay, so since we know the mass of the water, because we measure it out, right? We put it into the container, so we know its mass. We know the specific heat of water. That is something that you really should just know. So that's 4.184 joules per gram degree Celsius or Kelvin. And then we also can measure the temperature change. Then we can just use Q equals MCAT, and that's really how we do calorimetry. So big point here, and what makes calorimetry different than how we ended out last week, is that the energy change of the heat bath will be the same magnitude of energy as the chemical reaction or phase change, just with the opposite sign. Okay, that sounds kind of like a really complicated way of saying something, right? So let's talk about exactly what that means. So if heat is absorbed by a heat bath, okay, so we saw the temperature of the water go up. Okay, so if the temperature of our water goes up, where did that heat come from, right? So we know that the water absorbed heat because the temperature went up, but where did it come from? Well, it came from the reaction or the process that happened in the water, okay? So we would say that it was lost by the system, and so we've talked about this before where we have our system. So the heat is going to leave the system into the heat bath, which, like I said, we typically say is water. So if the temperature goes up, then that means that the system lost heat, or it released heat. So we say that our Q of that process is negative. Okay. However, if heat is released by the heat bath, so the heat is going to go from the heat bath into the system. So what we're going to observe here is that its temperature went down, then it was absorbed by the system. Okay, so we would say that it was absorbed by the system. So an absorption of heat or energy is going to mean that our Q is positive. Okay, remember that this is also relates to endothermic and exothermic reactions. We know that having or absorbing energy, if the system absorbs energy like this, then we would say that that is endothermic. And then if it is lost by the system or released by the system, then we would say that it is exothermic. So those are just some terms to make sure that you feel a little bit confident with there. So in class, or in this class, obviously we're not in class right now, but we're going to use a coffee cup calorimeter. And so typically what you have is you have a styrofoam coffee cup. And typically actually what you're going to do is have two of them. So I'm going to pretend like there's another styrofoam cup here. And we're just nesting them. And really the purpose of that is insulation, right? We want all heat that's released by a reaction to go into the water bath. We don't want it to escape into the surroundings. So we want something that is a good insulator, like a styrofoam cup, and nesting them provides a little bit of extra insulation. So the system is going to be in the water. You see that we also have a thermometer where we can measure the change in temperature. Now, what I want to figure there is that remember that a change in temperature is always going to be your final temperature minus your initial temperature. So it's always going to be it's always going to be final minus initial. All right, so I'm going to go through 3 types of problems. That does not mean that there are only 3 types of calorimetry problems, but that is all that I'm going to hit in this video today. The first type is to determine the specific heat of a metal. So it says that we have a 58 gram sample of metal, that it's at 100 degrees Celsius. Now the way that they typically would have done that is they would have had a test tube with the metal. So here's my metal. Okay, so they would have a test tube with the metal, and then they would put that test tube into boiling water. All of that metal would have been there, so that's boiling water. Since water boils at 100 degrees Celsius, then if we keep that test tube with the metal in there for long enough, the temperature of the metal should be 100 degrees Celsius. Okay, what they're going to do is then pour that metal into a calorimeter, which has 60 grams of water at 18 degrees Celsius. It says that the temperature of the water increases to 22 degrees Celsius. And then it asks us to determine the specific heat of the metal. Now, I don't have enough information about the metal to do any calculation with the metal first, but I do have enough information about the water. Okay, so I do have enough information about the water. So I know that my mass of water is 60 grams. I know my specific heat of water is 4.184. Okay, because it's always that. That's something you really just need to know. I know that my final temperature was 22 degrees Celsius and my initial temperature was 18 degrees Celsius. So my change in temperature, and I'm going to say W of the water, so that W is just standing for water, is going to be final minus initial. So that is 4 degrees Celsius. So what I can do is I can use my formula, which is Q equals MCAT. I am sweating, and I actually don't know why. Actually, I do. It's because I need to turn my AC back on because I turned it off earlier, but excuse the gross. Anyway, so for the mass of the water, we said that it is 60 grams. Now, you're going to see a problem in just a little bit where I add what dissolves in the water to the mass. I'm not going to do that here because that metal doesn't dissolve in the water. It's just going to be there and release its heat into the water. Okay, I'm going to plug in my specific heat capacity and I'm going to plug in my change in temperature. So then I'm going to multiply 60 times 4.184 times 4, and I get 1,004 joules. Okay, so that represents the heat that is absorbed by the water. Okay, and I know it's absorbed because I end up with a positive number there. So that means that the water absorbed it. So then I'm going to talk about the metal. Now what I know is that if the metal absorbed 1,004 joules, okay, so if the metal absorbed 1,004 joules, then if the water did, sorry, then I know that the metal released 1,004 joules. So the Q of the metal is actually negative 1,004 joules. Okay, so I'm going to plug in some information into Q equals MCAT. My Q is negative 1,004 joules. My mass of my metal is 58 grams. We are trying to find the specific heat capacity. And the change in the temperature of the metal is, it went to 22 degrees Celsius. That was the final temperature. And the initial temperature was 100. So I'm going to do 58 times 22 minus 100. And then I'm going to do the negative 1,004 divided by that. And I end up getting that my specific heat capacity is 0.22 joules per gram degree Celsius. If I were given a list of metals with their specific heat capacities, then I could then tell you which metal this probably is, right? So we would use this as a way to identify our metals. The next type that I'm going to look at is determining the enthalpy of dissolution of a salt. Now this is probably the most important part of the video for you because your assignment on Canvas has you doing this calculation, I believe, with 4 different salts. So this is an important one to kind of realize. So this one, it says that we have 25.7 grams sample of NaI, that it dissolves in 80 grams of water in a calorimeter. Temperature change is represented from 20.5 to 24.4 degrees Celsius, and it asks us to calculate the delta H for the process. So in a way, this is very, very similar to how we're going to do any kind of calorimetry problem or what we need to think about. So I mentioned this just a second ago, but when I'm doing my Q equals MCAT for my water, I didn't add the metal because it doesn't dissolve, but it says that the NaI actually dissolves in the water, and so I need to include it whenever I'm doing this calculation. So my mass is going to be 80 plus 25.7 grams. My specific heat of water is 4.184. Now, it does have NaI dissolved in it, so it might have actually changed the specific heat capacity of that solution. We're just going to assume it's the same as water. I probably should have put that in the problem, but that's going to be a very typical way to ask that question. And then we had a change in temperature as well, which I'm going to represent. So I'm gonna multiply and put all this stuff in here. And I got 1,725 joules. So that is the heat absorbed, because it's positive, by water. So my next step, so we call that, I guess, step 1. Step 2 is going to be to change the sign. Okay, so just like I did on the last problem, I'm going to change my sign. So I'm going to say my Q for the process of dissolution. So that was the energy dissolved by the water. So my Q of dissolution, the actual process of it dissolving, I'm just going to make that negative. Okay, and then the last thing, we don't have to do another Q equals MCAT here. The last thing is going to be to take our Q of dissolution and divide it by the moles of the solute. And that is going to give us our delta H of dissolution, which is what we're looking for on the lab as well. And so here we're going to take that negative 1,725 joules, and we are going to divide that by the moles of NaI, which I have not actually found. So that's 25.7 grams of NaI. Alexa, what is the molar mass of sodium iodide?
Sodium iodide's molar mass is 149.89 grams per mole.
Okay, sorry, I didn't have my periodic table over here with me. Oh my gosh, I am sweating like a freaking pig. Okay, so that's 25.7 divided by 149.89, which is 0.171 moles of NaI. And so my delta H of dissolution is going to end up being negative 10,087. Sig fig wise, I would say negative 10100, and that's joules. I probably would want that in kilojoules, so I'm going to divide that by 1,000 to get that to kilojoules, and that is per mole, since we divide it by moles. Okay, so that is the second type, and that is the way that you need to do it on your Canvas assignment. So that's pretty much the most important part of this video in terms of getting your assignment done for this week. The last thing is this Cheetos on fire problem. And I'm not gonna, I don't really wanna go through this. So I'm gonna kind of leave it there for you. So it's a little bit of an extra challenge. If you would like to do it and send it in to me, then I will take a look. But I will be in tutoring from 2 to 2:45, Monday through Friday. So hit me up in there if you have questions. And no further ado, my episode of One Hit Wonder. Let's paint the scene. It's 2013, springtime, time for tax review, and a teacher decided to make one of the biggest hits of all time. Today on One Hit Wonder, we have Corey Neiman. You may remember him from his hit single, Cheetos on Fire. Hello, welcome back to One Hit Wonder. With us today, we have hit singer, well, maybe not as much of a hit, because you were just a one-hit wonder, Mr. Corey Neiman. And you may remember him from his hit song, Cheetos on Fire. That was how long ago? It was 7 years ago, Joe. 7 years. Wow, it really just doesn't seem like it's even possible that it's been that long since Cheetos on Fire. That would have been, gosh, 2013. Maybe it kind of just feels that way because I start every morning with Cheetos on Fire, so it doesn't really seem like 7 full years have passed. So I got a question for you, Corey. All right, so you started your video, your music video, with a disclaimer, and it was a pretty long disclaimer, so just kind of curious what your thinking was behind including something like that. All right, Joe, I mean, that's a good question, and that's honestly a question that I get all the time, because, I mean, that disclaimer is about a minute long, right? And I think that what it really comes down to is I was only a second-year teacher, and while I still care about what my kids think about me, back then I really cared what they thought about me. And so when I had this idea to make Cheetos on Fire, and then I made it, and it was an interesting project, right? And so I wasn't really sure how it was going to be received by my students and really by the world, because it was a global premiere. And so I kind of decided to put that disclaimer to kind of, in a way, feel a little bit protected by it. What I've learned, though, in the 7 years since I've done Cheetos on Fire is that really you just got to be you, right? Be you and don't worry about anybody else, because, I mean, if you're not going to be you, then who else is going to be you, right? And so the haters gonna hate. All right, so Corey, speaking of haters, you did Cheetos on Fire 7 years ago, and you had tons and tons of success. But
right.
the reality is you never did anything else, and your haters say that maybe you just kind of got a little lucky. So let us know why you haven't done another project. Well, first of all, that kind of hurts my heart a little bit. I mean, to say that I was lucky, I mean, it was my work. It was something that I did put together and had that creative thought. I think that what can sometimes happen is when you start with a video that puts you on top, it's almost like you peaked too early. I didn't have the opportunity really to kind of grow into my career, and instead I just put out a masterpiece right at the beginning. Trying to come up with something that's not going to disrespect the Cheeto afterwards is kind of tough. So I've had some ideas. I've worked with some creative teams on those, but the ideas never really come together because, like I said, what can beat the flaming Cheeto? All right, so yeah, we definitely don't want to disrespect the Cheeto, right? So I think that the best place to go from here is to take a look at the video and have a little bit of commentary from our guest here. I am out for the day. I am Joe. Alright guys, so now that Joe is gone, I'm gonna let you in on some inside secrets behind the scenes of Cheetos on Fire. So I'm gonna cue that bad boy up at 1.5 speed and talk your ear off about my thoughts on Cheetos on Fire. Okay, so here it goes. So here you can see that I have that Cheeto and it is on fire. So we have the Dr. Pepper can, which is serving as a calorimeter. And you can see that it's not a very good calorimeter because you see all the heat that's getting exposed and it's releasing into the air. Some of it's also being absorbed by the can. Not really a great calorimeter, not really a great experiment, but it makes for an incredible song. And so one thing that you will see throughout the course of this video is just the same videos over and over looping. That's because 2013 Neiman was kind of lazy, although he might have been extra. I might have been extra. I was still kind of lazy, right? And so now I am still just as extra, if not more extra, but I would never ever loop a video like that. Oh, who is that? That brings up another point. Guys, 2013, I gave a teacher a camera. I said, do that, or I gave them my phone. I said, record it, and dumb old me had it like this. And so the result of that is 2 times wide and then about 0.75 height. So I look absolutely absurd. And so that's one of those things that's kind of tough for me to look at, because that's one of the things that I do hate about these videos. One thing that you also get to see is that right now I'm rapping, right, to the song. Here I am again. I'm gonna act like I'm all cool and stuff, right? I'm gonna light that Cheeto. 2013, I think I'm cool. I'm gonna pull off one of these. I'm like, hook 'em, which really hook 'em. And then, oh, I can't. I have my whole like, let's make it rain Cheetos, which is cool. Oh, ooh, it's my favorite part. So this is my favorite part, despite the fact that I'm, right? So other than that, this is my favorite part. Oh, here, oh, yeah, that's beautiful. Oh, yep. And here I go with my last part of this song. And kind of fun little ending. I was there late at night and I was exhausted from that. So yes, it's just a Cheeto and it's on fire. So that was this take of One Hit Wonders. I hope that you really enjoyed it because I enjoyed making it on the 7th anniversary of Cheetos on Fire. Hopefully it wasn't too extra or too much for you. Bye guys.